Thank you for inviting me in this seminar. So the title of this talk is Mathematics of Bose-Gas. So I'm going to begin with the very basic thing, the basic postulates of quantum mechanics. So, quantum mechanics in mathematics just means that we're going to consider wave function psi, which is an L2 of R3n. So we can just consider these particles are the coordinates or the points of R3, and we have n particles. So the space is L2 of R3n, which is just a Hilbert space. And we also want to consider Hamiltonian H, which is in general looks like this. So the quantum mechanics is to describe the property or characteristic of this wave function psi by using this Hamiltonian. And there are two different ways of using it. The first one is time-independent Schrodinger equation, which is H psi equals E psi. This is just an eigenvalue equation, so E is an eigenvalue of this Hamiltonian. And the other way of using it is time-dependent Schrodinger equation, which is I partial t psi t equals H psi t. So, the evolution of this psi wave function is governed by this Hamiltonian H. So, the title was Mathematics of Bose-Gas, so I think I should introduce what Bose-Gas means. So, consider a two-particle wave function f. And then we can define the permutation operator P by the equation like this. Pf is Pf of x1, x2 is f of x2 and x1. Then, because this is just the permutation of x1 and x2, if you act this operator P twice on the same function, then we get the original function f, which means that P squared is always unity. P squared is I. And we also have the Hamiltonian, which looks like this. So this Hamiltonian contains these Laplacians, which we call kinetic energy, and this U of xi, which we call potential energy or external potential, to be more precise. And the last term, V of xi minus xj, which we call interaction potential. But all those three terms are symmetric under the permutation of particles. So if we just change the role of x1 and x2, then the Hamiltonian stays the same. It means that if we perform this P permutation operator, then Pf will be almost the same as f. There can be one difference, and the difference can come from this fact. So if you have this Hamiltonian like this, and if you consider f and hf, this notation means just in the product in the given space, then this will give us the first, the summation of the kinetic energy terms. The kinetic energy terms of gradient I squared, this is after the integration by parts. This plus the second terms, external potential. And finally, the V terms, interaction terms. But, because of the structure of this inner product, we always have this absolute value squared whenever we have this energy. Which means, this Pf does not necessarily be this f, but it can contain a small factor like e to the I theta. So Pf can be e to the I theta times f for real theta, because in this case, this absolute value of f is always the same. So we have two information. One is the p squared equals I, and the second one is the pf is almost like this, but we have e to the I theta. And putting those information together, we can conclude that p equals I or minus I. I is a unity. So there are only two different ways of having wave function. The first one is p equals I, unity. And in this case, we call this wave function is symmetric. And the system is what we call the Bose system. And we say the system obeys Bose-Einstein statistics. And those type of particles are what we call bosons. And for antisymmetric case, well, when p is minus unity, we say the wave function is antisymmetric, the system obeys Fermi-Dirac statistics, and the particles are fermions. Yeah, of course. Yeah, just renaming. Yeah. And so physically, they should look the same. So well, to understand the Bose-Einstein condensation, which is kind of holy grail of this topic, we can assume that this Hn is without this interaction term V. So well, we just assume that this Hn contains these kinetic energy terms plus external potential. Then, if you let this phi is the ground state of this one particle Hamiltonian minus Laplacian plus u, well, sometimes we can explicitly calculate this phi, the ground state of this one particle Hamiltonian. For example, when you have Coulomb potential, then it becomes the spherical Bessel functions. Then the ground state of this Hn, the n particle Hamiltonian, becomes just the tensor product of phi tensor n. So, well, in other words, if Hn psi equals E psi with the lowest eigenvalue, then this psi is just nothing more than the product of this n phi's. Okay, but then, well, we had two different cases. One is symmetric, and the other was antisymmetric. If you have this type of function, product functions, then it always is a symmetric function. So, well, this ground state can only happen for bosons, the Bose systems. And, well, psi is a symmetric function, hence the boson system. And this is the simplest example of Bose-Einstein condensation, which is just people say BEC, where a macroscopic occupation of single one-particle state occurs. So if we want to know the physical properties of this psi, the ground state, then we only need to know this one particle ground state, and every particle is in the same state, the same ground state. So this is very important phenomenon in physics. And in 1995, this is observed experimentally. And so this becomes very famous object in mathematical physics as well. So this Bose-Einstein condensation is very important, and that's why we're going to focus on bosons. So well, if there's no interaction potentials, everything is easy. But if we put this interaction term, V of xi minus xj, then everything is complicated, and in fact, well, almost no result on the Bose-Einstein condensation is proved for this case with interaction potentials. And we want to study ground state energy to understand BEC, Bose-Einstein condensation. So, well, I'm not going to explain why they are closely related, but, well, in very few known cases of the proof of Bose-Einstein condensation in mathematical physics, they always need to use the property or the exact value or the methods of finding ground state energy. So, well, to have a framework to understand this ground state energy, we're going to consider a system in which the particles are in lambda, which is a cubic box of side length L in R3. And you're going to consider the thermodynamic limit, which means n, the number of particles, and the side length L tend to infinity, while the density N over L cubed is fixed. Later, we also want to put this limit on this system, low density limit or dilute limit, which means the rho is very small, the density is very small. And for simplicity, we only want to consider the potential vanishes after a certain length. And well, in most of cases, we will also only consider V is non-negative or repulsive in physical meaning. So the typical shape of V looks like this. So V, this is X. So V always stays positive, and it vanishes after a certain point. And this is R0 in this notation. And we want to find the ground state energy, or the lowest eigenvalue of the Schrodinger equation in the system of n particles in the lambda whose side length is L. Heuristically, we can find the ground state energy very easily. But first of all, to understand the argument or the answer itself, we need to know the concept of scattering length. So the scattering length comes from the zero energy scattering solution, which satisfies this equation. So this V is the interaction potential V, and note that we have 1/2 here instead of just V. And minus Laplacian plus 1/2 V equals 0. With the normalization such that the limit of phi of x as x tends to infinity equals 1. So why is it 1? Because, well, the general solution of this equation looks always like this 1 minus, well, the constant minus constant over R. So well, in the basic PDE argument, we know that if we have an equation like Laplacian of f equals 0, then we have two linearly independent solutions. One is constant, or is constant over R. And the linear combination of those two also is the solution of this. Laplacian equals 0. But then, well, V will vanish eventually. So in that region, we only have this Laplacian phi equals 0. So the solution will look like C1 plus C2 over X. And with this normalization condition, the C1 will become 1. So, well, we can just think about this phi to be, well, 1 minus A over X in this region. And this A is what I call the scattering length of interaction potential V. So for example, if V is a hardcore potential, such that V is infinity here in this region, and it just vanishes after that. Okay. In this case, we need to have the function to be 0 in this region, because, well, otherwise this V is infinity, so the equation doesn't make sense. And, well, in this region, the solution will be 1 minus A over X. Okay. And then here, well, so suppose that we have this B. But still, at B, this must be 0. So this B should be A. So the shape will look like this. And this is a solution of this zero energy scattering equation for this hardcore potential. Then we can give a meaning to this scattering length such that this A means that if we have this potential V, then we want to consider this potential as a hardcore potential like this. So, well, when you calculate the ground state energy, the leading term or the second order term for this B is just the same as the ground state energy of this hardcore potential case. So, well, so in other words, if you have this B potential term, then every other information just vanishes, except the scattering length of interaction potential. So here's the heuristic argument. So suppose that we only have two particles in the ball of radius r, and then we can guess that the ground state is very close to phi of x1 minus x2. So well, so this phi was the solution of this zero energy scattering equation, and we say that, well, this is zero. The energy is very low. So the ground state will be very close to this phi. Okay, what happens if we calculate the energy with this phi? Well, you may think that this will give us zero energy because this is zero energy scattering solution. But there's one problem. The problem is that when you consider this minus Laplacian, we also need to specify the boundary conditions. Well, because this Laplacian is not a symmetric or Hermitian operator. And, well, so the calculation is like this. So for the two-particle system, we have we have the gradient 1 phi squared, gradient 2 phi squared, b x1 minus x2 phi, and also this is x1 minus x2 squared. Integration. The problem is that, well, we can rewrite this B by using the zero energy scattering equation so that the minus Laplacian plus 1 half B phi 0, or V phi equals 2 times Laplacian phi. What happens if you use this equation here? Well, this V phi square will become phi bar times Laplacian phi. So, if you can use integration by parts, then this phi bar times Laplacian phi will generate gradient phi times gradient phi with a different sign. So, in this thing, this B phi square will cancel this term. But here the only problem is that when you use the integration by parts, we also have the boundary terms. So the boundary, so well, if you have this plus this, then this will make this boundary terms, and note that the region is x equals r. So we only consider the boundary of the ball. And, well, after this moment, this is just a calculation. So we have 4 pi r squared times this 2. And this phi was, well, 1 minus a over r, when r is very large. So 1 minus a over r for this phi. And finally, this gradient phi is just a over r squared. And when r is very large, this 1 minus a over r will become just 1. So we have a pi r squared times a over r squared, which is a pi a. So, if we want to find the ground state energy for this two-particle system in the ball, then it approximately is this over this. So, well, the energy always should be the inner product with respect to h, the expectation value, over the norm squared. So we also need to calculate this term in the denominator. And, well, this is the case because, well, in usual cases, we only consider the normalized wave functions. But in this case, we have different type of normalization such that this will tend to 1. So, well, we also need to calculate this thing. And if you calculate this thing, then this will become a pi a over this 4/3 pi r cubed, which corresponds to the volume of this sphere, or the ball. And, well, so it's not exactly the same as this thing, but it converges to this thing because, well, phi is not exactly 1, but it is close to 1. So, well, we have the 1 minus a over x, but, well, because x will be mostly large in this ball when compared with a. So this is almost like 1, so, well. Anyway, so this is just a heuristic argument. So we have a pi a over volume for 2-particle case. What about n-particle system? Well, we need to consider 2 things. First, when you have n-particle system in this cubic box of side length L, then the probability of having a given pair of particles in the ball of radius r is this volume, the volume of the ball, divided by the total volume of the box. So this means that if you have a large box of side length L, then if you consider a pair of particles, x1 and x2, then that probability means having the probability of having this particle inside the ball of radius r centered at x1. Okay. So this is probability. And we have n times n minus 1, choose 2 such pairs. So energy, the probability, times number of pairs. Then the volume will be cancelled out. So we have 4 pi a pi a over 2, and n squared over L cubed, which is 4 pi a, n over A cubed was rho, so 4 pi a rho times the number of particles n. So this is heuristics. This is not a rigorous proof, because there are so many pitfalls or flaws in this argument. But nevertheless, it gives the correct first term. So in mathematical physics, we want to justify every step of the heuristic argument in a mathematically correct way. So the perturbation is needed because, well, you may notice that in the previous heuristic calculation, we implicitly assumed that the particles are almost uniformly, evenly distributed. That's why I could say the probability of having a given pair of particles in a ball radius r is this over this. If the distribution is somehow very weird, then this probability doesn't make sense. But then, how could we use that kind of argument of having the probability like that? So that comes from the perturbation. So, well, you may think the perturbation is only for physicists because this is not rigorous and this, well, contains some infinite series which doesn't make sense in mathematics. But actually, mathematicians can use perturbation in many different ways. One of them is using the Temple's inequality, like this. So the final form of the Temple's inequality is this, but I'm going to show you how we can use this. So this is very simple. Consider an operator H, which is the sum of H0 and V. If we let E0 and E1 be the two lowest eigenvalues of H, the whole thing, then we have an operator inequality that H minus E0 times H minus E1 is positive. So, well, when you say the operator is always positive, it means that whatever state we have, the expectation of this value with respect to that state is positive. So in this case, we want to use the expectation value with respect to the ground state of H0. So now it becomes very similar to the perturbation of physicists. So we're going to find the ground, well, we're going to use this H minus E0 times H minus E1 with respect to the ground state of H0. So we have this thing. If we just expand this, then we have H squared minus E0 H0, E1 H0, and E0 plus E1. And after some manipulation, we can get a bound. E0 is bigger than this H0 minus this thing. Okay. In this case of So in this case of Hamiltonian, if you assume that this is H0, then the ground state of this operator is just a constant, because that gives 0. And this minus Laplacian is always positive, because minus Laplacian always becomes the gradient f squared. So this is always positive. That's why this minus Laplacian is always positive. So we have this operator whose ground state is just constant. And the remaining things are just V in the perturbation argument or the Temple's inequality. So if you just imagine that we're using the ground state or the constant wave function for this 0, then, well, this H, the expectation of H will become just V of something, and this thing. And if E1 is much larger than H0, so that the denominator here is very large, then this, the second term, will be an error term. So the ground state is almost like this H of 0, the expectation value of H with respect to the ground state of H0. And that's what we have done in the argument, the heuristic argument, to find the ground state. So, well, if the function is just constant, then the probability is just uniformly distributed. So that's why we could use that argument. So, well, in the actual proof, well, so this is just a technical thing, but in the actual proof of the ground state energy, we use E10, which is the second lowest eigenvalue of H0, instead of this E1, because, well, first of all, E1 is hard to find, because it contains V. And secondly, if you have E10 instead of E1, then, well, E10 is smaller than this E1. So this thing becomes large, and this becomes smaller. And if you have a small thing, then this is, well, of course this is worse lower bound, but still the right lower bound. And, well, here's some history. And, well, this, at least these two slides are exactly the same as the slides that I used in the last time. So I'm just going to tell it very quickly. So the Bogle review was the first one who analyzed the system of interacting bosons instead of just non-interacting bosons without V. And Li and Yang, the physicists, derived the ground state energy per particles in the low density limit. And, well, 4 pi rho plus blah, blah, blah. So physicists have this formula in 53 years ago. And Dyson, who is generally regarded as the first mathematical physicist in this sense, proved that E0, the ground state energy per particle, is less than this, and this is bigger than this. So, well, the right answer should be 4 pi 8 rho times 1 plus this thing. This thing should be the right answer. this thing is a little worse than this, because rho is very small, so the rho to the 1/3 is larger than this, and if the upper bound is larger than this, then the upper bound is bad one. The lower bound is much smaller than this, because it has an additional factor of 1/10 square root of 2. And almost for 40 years, there were no improvement in this topic. And Lieb and Ingbersen in 1998 proved that this is bigger than this, with very bad second order term, rho to the 1/117. But nevertheless, the first term, the leading term, was right. So we could say that the ground state energy per particle is 4 pi rho in the leading term, up to the leading term. And of course, well, this result is kind of nonsense in mathematics. And well, there are some different results. So the first one is proven by myself in 2009 that so far we only consider this type of potential, and well, of course there are many different types of potentials. So if you have something different like this, which contains very small negative part here, then still the leading term is 4 pi 8 rho. Well, the second order is pretty bad. But still, we can prove this thing. And Yao and Yin proved that the upper bound is correct up to the second order term. And in 2009, Yin and myself proved that this E0 is larger than this, rho to the 1/3. And well, I know that there are a large gap between this rho to the 1/3 and this rho to the 1/2 and rho to the 1/3 are pretty different in this subject. But nevertheless, this is so far the best result. Previously, the best result was 1/17. Okay. So, to prove the ground state energy, we need to prove two different things, upper bound and the lower bound. If they are the same, then we can say that we have this lower bound, this ground state energy. So the upper bound calculation is always easy. You only need to find a good wave function, just one. It is because this. So well, whatever psi we have, this must be larger than this E0 time, just E0, the ground state energy. So what we need to do is to find a very good psi, which is very close to ground state. And then this value, what we can get, that we can get from the calculation, is just an upper bound. So well, E0 is less than this. So this is an upper bound. Okay, so there are too many different ways of constructing an upper bound. And what I'm going to show you is one of the worst things. So, well, to construct the trial function, psi, we let this omega with the eigenfunction with the lowest eigenvalue E0 with this operator, minus the Laplacian plus 1/2 v. So that minus Laplacian plus 1/2 v times omega is E0 omega. And, well, I think the most natural way of finding a trial wave function is to have this product type of wave function. So we just multiply all of them, the product of this omega, xi minus xj, for all different pairs of I and j. And, well, just for notation, we use abbreviations like omega ij is omega xi minus xj in gradient and Laplacians and v as well. Then, well, so this is just a calculation. So minus Laplacian k will make two different type of terms. So, well, this Laplacian is just twofold, twice differentiation. If this Laplacian hits the same omega twice, then it will become minus Laplacian omega. if this Laplacian hits different omegas in this product, then it becomes gradient times gradient. So we have these first terms and the second terms. Okay. That means if you have this total Hamiltonian, h sub n, then it will generate these terms from the Laplacian calculation, plus this 1/2 v. So now you can see why 1/2 was needed, because well, in this case we sum over different I and k, not just pairs, but different I and k. But then this v should be with 1/2. So well, this minus Laplacian plus 1/2 v is, well, the Hamiltonian that we have seen from this zero energy scattering solution. So well, this term will become almost like this 8 pi a over volume, or well, in this case this should be 4 pi a, because we had this 2 times the ground state, this integration, but we don't have this 2 in the upper bound calculation. So without this 2, it becomes 4 pi a over 4/3 pi r cubed. So this becomes 3a over r cubed, 4 pi a over 4/3, 3a over r cubed. And, well, the second term will be an error term, which means that the second term will be much smaller than this first term when you calculate it correctly. So I'm just going to skip the calculation for the second term because of the time limit. But anyhow, so well, this will become very small, so we only focus on this first term. Then it becomes 3a over r cubed times, so well, psi square. Why we have psi square? Because well, we calculated this psi to the minus 1 times hm psi only. But if you have psi times hm psi, then this becomes psi squared times this thing. So psi squared times this thing, and this thing will become minus Laplacian omega ik plus 1/2 v ik omega ik, this is 0 omega ik, and after having this 1 over omega ik, this omega ik will be cancelled, so we only have E0 as long as the distance between xi and xk is less than r. So this omega was the eigenfunction with the lowest eigenvalue E0 on the Bowler radius r. So xi, if xi and the distance between xi and xj is bigger than r, this omega will just become 1, and we don't have anything. So this thing plus error term comes from this. And to get an estimate, the technique of finding this integral, the chi ij times psi square, is, well, so just assume that we have 1 and 2, and then this chi ij times this omega ij squared, well, this psi was the product of omega ij's, and then so well, we have omega 1j's, and we have omega 2j's, and we have omega ij's. And, well, I didn't prove this thing, but omega is always less than or equal to 1. So that if we just ignore these two things, then, well, because this was less than or equal to 1, if we ignore those two things, then it becomes larger. So this chi 1, 2 omega ij squared. We can just perform the first two integrations with respect to x1 and x2 so that this is less than chi1, 2 times the other things. Omega ij squared and ij is bigger than or equal to 3. Okay, so well, we ignore this, and this will become larger. This chi ij integration is very simple because, well, this is by definition 1 when those two particles are in between this distance, r. So that if you just fix one particle, then the first integration will make this 4 pi r cubed over 3. This is the volume of the ball of radius r. And we just have freedom to choose the position of the second particle. So this will make L cubed, which is the total volume of the box. So this times the remaining integrations. We don't perform this integration. And of course, we also need to find this something in the denominator. So, well, the same idea, but except that now, if we just ignore this and this, then it will become smaller. It will become larger. So we also need to think about some error terms. And, well, again, I'm not going to describe the details of these error estimates. But, well, up to these error things, we can just ignore these two things. And after that, this psi-square integration will become this thing, the same manner, and we can perform. So in this case, the idea is like this. We have the product of omega ij's squared, and this is bigger than or equal to product of omega ij's, and ij is bigger than or equal to 3 plus some error. And this 1 means that we want to integrate with respect to the first particle and the second particle. If you integrate with respect to the second particle and the first particle, then it just becomes L cubed. L to the 6th. So L to the 6th times this integration. And therefore, this is bounded by, well, n times n minus 1, which comes from the fact that we only considered chi 1, 2, but we actually needed to sum over different ij's. So we have n times n minus 1 times, well, 3a over r cubed, which was here. And this 4 pi r cubed over 3 times L cubed over this L to the 6th, this final factor. And, well, after calculation, well, everything will be cancelled except 4 pi a rho n. So this is how we get the upper bound. And the error term in this case, well, if you calculate in detail, then you can get the error bound is so 4 pi a rho n times 1 plus rho to the 1/4. So 1/4 is pretty bad because in 1957 Dyson even knew that this can be 1/3. And currently the best result or the correct result is 1/2. So, well, A is not terribly important in this calculation because we just consider A is just a constant. A does not change. So, well, if we want to have this precise constant, 128 over 15 square root of pi, then we need to include this A in the calculation. So that was the case for this paper. Because, well, so when you can have this exact constant, then you need to include this A. But otherwise, it's not very important because we only know this kind of weak lower bound. Okay, the final thing is the lower bound calculation, but this is very different from the upper bound calculation. So for the upper bound, we only need to have a good trial function. But in the lower bound, we actually need to follow the heuristic argument. So in the heuristic argument, we implicitly assumed that we can use the perturbation, so that having a particle in some position has the uniform probability. So the distribution of the particles is just uniform, evenly distributed. But then how can we use the perturbation? Well, the problem is that when you use the perturbation, we have E1 minus H, and this E1 must be much larger than this H. But then when you have this box, E0, 0, which is the ground state of this H0, the kinetic energy is 0 when you have the constant wave function. The first lowest eigenvalue, or the first excited state, has the energy one by squared. So, well, if you study some quantum mechanics or the calculation like this, then in three-dimensional, you have sine over 2 pi x times L and constant. Well, I think you know that this type of the calculations. So, if you just add this kind of thing, then the energy will increase a little bit, but then that energy will be proportional to L 1 by squared for L3 minus 2. This is very small when L tends to infinity. So the key concept is to convert V into something different. So what is the problem? Well, we have this H0. This is nothing more than this V times some, this V. So, well, V is fixed like this. When L becomes very large, this E10 will become very small, so that the perturbation doesn't make sense. So what we want to do is to flatten V. So this should be changed into this kind of potential. Very small, but long range. So that's how we do it. So again, I'm not going to prove this Dyson's lemma, but Dyson's lemma says that if you have this kinetic energy plus 1/2 V, then this is bigger than or equal to this string length of V times this U. And U has only has to be positive, and the integration of U is less than 1, and U is 0 inside the region where R is less than A. And then we have freedom to choose U as long as U satisfies these conditions. So we're going to choose this type of U. So that's what Dyson did in his paper in 1950s. And well, that means if we sacrifice this kinetic energy, we can convert these interaction potentials to something different, so that H is bigger than a new operator, W, which is described or written by this U, the new interaction potential. And Lieb and Ingwersen in 1998 used a different idea. Anyway, if we used this argument and sacrificed all the kinetic energy, we cannot use perturbation because we don't have any kinetic energy. So what they did was to keep a little portion of the kinetic energy, epsilon, and convert everything else into this W with new interaction potential. So that we have this kinetic energy term like this plus this. And then this kinetic energy term is saved, and you can use the perturbation by using this kinetic energy. So that, well, E0 is now like this, and, well, this is template inequality that I showed you in the perturbation argument. Still there's a problem because, well, still we have E1, 0, and no matter how flattened U we have, L becomes infinity eventually, so this will tend to 0. So perturbation always fails. So, well, yes, so here's the argument. So, well, so E0 will always become much smaller than this W0 as long as when L is too large. So to avoid the dilemma, Levin and Ingves used the cell method where they first divided this box into smaller cells. So like this. And perturbation is applied only in this small cell. And instead, increasing the side length of this box, we can just increase the number of cells. So that was the key argument. And for calculation purpose, we may use this thing, but we can just ignore this calculation. So in each cubic cell of side length L, small l instead of large L, contains n particles, small n instead of large n. Then the ground state energy of the system of n particles in this small cell is 4 pi a over L cubed n times ms1. So this has the same structure with this 4 pi a times n times ms1 over L cubed. So 4 pi a times n times ms1 over L cubed plus some errors. And then we want to minimize the total energy, which is the sum of the ground state energy over all small cubic cells. And, well, you can see that this n times ms1 is convex. So you can use the Jensen's inequality, or, well, there are too many different ways of minimizing these functions over the cells, but anyhow, the minimum is attained when particles are evenly distributed. So when n is rho times L cubed, the rho is density of the whole box, the large box. So in this case, this leads to this total energy is L cubed over L cubed with the number of cells times this 4 pi over L cubed times n times ms1, but n is rho L cubed, rho L cubed. And if you calculate like this, rho L cubed will cancelled. We have 4 pi rho times L cubed, which is 4 pi rho L. So again, the same result. And if we calculate this error, and, well, there are too many different errors. So first of all, in this cell method, we simply ignore the interaction between this and this. So this grid is kind of imaginary. It does not exist in the real world. But nevertheless, we just calculate the energy in this cell and in this cell and take the sum. But in this case, we are ignoring the interaction between particles which are near the boundary. So this will, well, make some errors in the calculation, and also in the, well, the perturbation argument or the template inequality, we also have some errors and, well, some other things. And after calculation, we can see that this argument will give us this minus c times root 1 17. And, well, to get a better results like this or this, well, for this we need to construct a totally different trial wave function. And also for this case, well, we need to use several different ideas to find that root 3 1/3 instead of 1/17. So I think, yeah, basically this is the end of the talk. So thank you for listening.
I have two questions.
Yeah.